Particle in a box, boundary conditions, and the Schrödinger equation. Now, what is Schrödinger equation? Well, for any particle that has a wave characteristic, we have a wave equation. And the wave equation for electromagnetic waves, electromagnetic radiation, which consists of photons that carry energy packets of HF, is given by Maxwell's equations. So that's the subject of this course. At the beginning, we talked about these electromagnetic waves, which are described by Maxwell's equations. Now, the corresponding wave equation for material particles which have non-zero rest energy is given by the Schrödinger equation. So the Schrödinger equation replaces Maxwell's equations in the case of particle waves. Okay. So for a particle of mass m, confined to move along the x-axis and subject to a potential energy U of x, this wave equation is the time-independent Schrödinger equation, that is minus h bar squared divided by twice the mass of the particle, second derivative of the wave function with respect to x, plus potential energy times the wave function is equal to energy times the wave function. So this is basically E, the total energy of the system. Okay, so that's the wave equation for material particles. So if we have the potential energy U as a function of x is known, one can solve it to determine the wave function psi and allowed energies of the system. So if you have the wave equation, the time-independent Schrödinger equation, and if you know the potential energy profile, you can solve this equation for psi and you can obtain the corresponding energy levels of the system. So there are some conditions the wave function psi must satisfy in order to be a solution of the Schrödinger's equation. The first condition we have already talked about is that the wave function must be normalizable. What does that mean? If I integrate from minus infinity to plus infinity absolute value of psi squared dx, in other words, if I look at bra cat psi, this should be equal to 1. So this is our normalization condition. The wave function must go to 0 as x goes to plus or minus infinity and remain finite as x goes to 0. So the wave function should not blow up. It should approach 0 as x goes to plus or minus infinity and must remain finite as x goes to 0. So we need a normalizable finite wave function which decays to 0 as x goes to plus or minus infinity. The wave function must be a continuous function and single valued. What does that mean? Well, it doesn't have any discrete values, so it always has a finite value for a given position, and it is single valued. So if you have a position x naught, let's say, psi of x naught cannot have more than one value. So there's only one value that corresponds to one value of the position. So it's single valued. The derivative of psi must be finite, continuous, and single valued everywhere for finite potential energy. So the derivative of the wave function is also finite, continuous, and single valued if the potential energy is finite. And this is useful in explaining the behavior of atomic and nuclear systems. We can solve for all atomic and nuclear particles the wave function and look at the characteristic behavior of these systems based on this wave function. And we can calculate the probabilities of probability distributions for the particles as a function of their position. Okay, so we have talked about the wave equation that is used for material particles, that is replacing Maxwell's equations for electromagnetic waves. It's the Schrödinger equation. For a particle with mass m that is confined to move along the x-axis in one dimension and subject to a potential energy u of x, the total energy times the wave function is potential energy times psi plus minus h bar squared over 2m second derivative of the wave function with respect to x. H bar is Planck's constant, h divided by 2 pi, so that's h divided by 2 pi. And this is basically the kinetic energy term here. It's the time-independent Schrödinger equation. There is no time dependence. The wave function, we only have the spatial part, x dependence. If you know the potential energy profile as a function of x, we can solve this equation to find the wave function and the corresponding energy levels. We will see an example in the next lecture. The wave function must satisfy a set of conditions to be a solution of the Schrödinger's equation. It must be normalizable, it must be finite and remain finite as x goes to 0, and it must go to 0 as x goes to infinity. It should be a continuous and single-valued function. Its derivative must be finite, continuous, and single-valued everywhere for a finite potential energy. And we can solve Schrödinger's equation, obtain the wave function and probability distributions to explain the behavior of atomic and nuclear systems.